Ok, stiamo registrando. And let me share the slides. Ok, vedete le slide?
Sì.
Benissimo. Okay, so we can start. Okay, so yesterday we introduced the theory of quantum chromodynamics, which is the quantum field theory of strong interactions. We somehow derived the Qcd Lagrangian following the same step that we used to derive the Qad Lagrangian. And also we went into some detail in the quark-gluon interaction. We defined the core factors, how to calculate the matrix element for a 3-level Qcd process, etc. So today we will instead focus more on the phenomenology of Qcd. So as you see here in the slide, I report here as you recognize, the two families of charmonium on the left and the bottomonium on the right. So as you know, these are bound state of C bar and BB bar quarks, which are essentially denoted as heavy mesons. Now, differently from the up, down, and strange quarks in the light mesons, the velocities of the heavy quarks in these heavy mesons, so the charmonium and bottomonium states, is relatively low. So the beta for the charm quark is order of 0.3, and for the bottom quark is only 0.1. So essentially only 10% of the speed of light. And so the observed spectra that you see here can be well described by Qcd potential in the non-relativistic approximation. So in other words, since heavy quarks are moving relatively slow, a non-relativistic approach is justified and also quite accurate. And this is what we call the non-relativistic Qcd approach. So in non-relativistic Qcd, the quark-quark and quark-antiquark interaction are expressed by a static potential, okay, that you can actually put in your Schrödinger equation, the non-relativistic equation of motion. And as we have seen yesterday, due to the gluon self-interaction, the potential at large distances is proportional to the quark separations. So it is proportional to R, where K is the string tension, which is of the order of 1 GeV over Fermi cube. Now, what about now the short distance component? So this is the long distance component, long for quark pair or quark antiquark pair. So what about the short distance? So here in the non-relativistic Qcd approach, one essentially takes an analogy with respect to the Qad case. So in particular with the non-relativistic Qad limit, so the Coulomb potential. The Coulomb potential, as you know, is in this form, where the plus means repulsion, and this is the case of same charges, and the minus is attraction for opposite charges. So in complete analogy to this, the short distance Qcd potential is chosen in this way, okay? So essentially the same shape, of course corrected by the proper color factor, the one that we defined yesterday, okay? And the plus or minus depends on, indeed, if they are the same charge, so essentially quark-quark, or opposite charge, quark-antiquark, where in this case the charge is the color charge, of course. Now, so let's make use now of the totally symmetric color wave function of mesons, the one that we introduced yesterday. So this is the totally symmetric singlet color component of wave function of mesons. And let's calculate the expectation value of this non-relativistic Qcd potential for the case of heavy mesons. Okay. So let me switch now to the board. All right. So let me write down again the wave function. The wave function, the color wave function component for meson, so Q bar states. So this is 1 over square root of 3, red anti-red, plus green anti-green, plus blue anti-blue. It is totally symmetric under the exchange of any color pairs. And now we can evaluate the expectation value of this static Qcd potential by making use of this wave function. So essentially what we want to do is to calculate this quantity. And so more explicitly, we have 1/3, which is the square root of 1 square root of 3. Then we have red anti-red plus green anti-green plus blue anti-blue. Then we have our potential. And then we have again red anti-red plus green anti-green plus blue anti-blue. Now we can make this more explicit. So this is 1/3, and then we have all the possible combinations. So it's red anti-red, VQCD, red anti-red, plus second term, red anti-red, VQCD, green anti-green, etc. And then the last one will be blue anti-blue, VQCD, blue anti-blue. Okay. Now we make use of the analogy with the Coulomb potential that I was showing before in the slide, okay? And this we do separately for each of these contributions. So for instance, let's take the first one, red anti-red, VQCD, red anti-red. In this case, one has minus, because it is a quark-anti-quark pair. Then we have our color factor for red anti-red into red anti-red. And then we have alpha strong divided by R, which is the Coulomb-like potential shape. Okay, and this is of course the same for all the three diagonal terms. Which corresponds to the first category for what concerns the color factor, as we studied yesterday. Okay, then we have also the mixed case. So for instance, red anti-red, VQCD, blue anti-blue. This is minus C, red anti-red into blue anti-blue, alpha S divided by R, etc. Okay. In this case, this is the same for all the 6 non-diagonal terms, and this corresponds to the third category that we analyzed yesterday. Okay. So now we can replace everything into our expectation value. So the expectation value of VQ bar will be minus alpha S divided by 3R. And then we have the color factor for red anti-red into red anti-red, plus etc. Plus, for instance, the color factor of red anti-red, this we don't have here, into blue anti-blue, etc. All 9 terms here. Okay. Now we can replace. We can merge the color factors for the 2 categories that are contributing here. So this is minus alpha S divided by 3R. And then we have 3 times the color factor for the first category, that is red anti-red into red anti-red. So the 3 diagonal element plus 6 times the color factor for the non-diagonal elements, which corresponds to the third category, red anti-red into blue anti-blue, for instance. As we've seen yesterday, they are all the same for each category. And so we have minus alpha S divided by 3R. And then we have 3 times 1/3, as we calculated yesterday, plus 6 times 1/2. And the result of this is minus 4 divided by 3, and then alpha strong divided by R. And so we can write down now our phenomenological non-relativistic potential for QQ bar systems, which is our essentially non-relativistic QCD potential, as the short distance component that we just derived, so 4 divided by 3 alpha S R, plus the long distance component that we introduced already yesterday, and which arises from the gluon self-interaction. Okay. All right. If this is clear, then we can move back to the slides. And we can comment more on this. Okay, so this is the full shape of our non-relativistic QCD potential. And you see here the Coulomb term, which is important at low distances. This is the distance, of course, in the x-axis. And then as soon as the distance between the two, the quark-antiquark pair becomes large, then the linear term dominates, okay? And this, at the end, will dominate at larger distances. This is an example of evaluation of this potential for a value of alpha strong of 0.2. Now, this potential has been extensively used to obtain predictions for the spectra of the charmonium and bothonium. If you remember, yesterday I showed you the charmonium states when I was introducing the exotic hadrons, and I showed you that there are observed states, the majority, but also predicted states which are not yet observed. And the predicted states have been obtained essentially by using this kind of potential here. Now, this approximation is relatively good for the charmonium case, but it is even better for the case of bothonium states, because as we've seen before, the bottom quarks are, of course, heavier, and so they move even slower. And so the non-relativistic approximation works even better for the case of boson anti-boson. And so one obtains, of course, more accurate prediction for the case of bothonium. In particular, the best agreement with data is found using this value of the string tension, so 1 GeV over Fermi, providing further evidence of the presence of a linear term in the potential, one is here, okay, which is the one responsible, as we've seen, for the color confinement. Okay. Now, let's now move on to the hadronization process. Okay, so suppose we are now working at the Eplasimire collider, okay, and so we have, and in each, in a certain Eplasimire collision, we produce a quark-antiquark pair, okay? So we want to study now how these quark-antiquark evolve in space and in time, and what at the end we will detect with our detector, okay? So the two initially free high-energy quarks are produced back-to-back, okay, in order to ensure momentum conservation in the center of mass system. So suppose we have your beam of a positron and electron, which collide here, and then you produce a back-to-back pair of quark-antiquark. Now, as we have seen yesterday, as the quarks separate, the gluon field is squeezed to a flux tube with an energy density of 1 GeV over Fermi, okay? Now, what happens when the distance between quark-antiquark increases even further? So this is, let's say, a step forward with respect to what we discussed yesterday. So as the separation increases, the energy which is stored in the color field becomes sufficient to create a new quark-antiquark pair, essentially from the vacuum, okay? And in this process, the original color field breaks into two smaller strings, okay? So if the energy of this quark-antiquark pair is sufficiently large, as soon as they get far away, the string breaks and a new quark-antiquark pair is formed. But now we have two new strings, okay? And the process, of course, continues, okay? As long as quarks and antiquarks have enough energy, further quark-antiquark pairs are created in this way. This is a pure perturbative process, QCD perturbative process. Now, when does the process stop? Of course, the process stops when the energies of quarks and antiquarks goes below the threshold for new string breaks, okay? At a certain point, each time you create a quark-antiquark, you are spending energy, okay? So the more quark-antiquark pair you create, the lower energy they have, and at a certain point, this energy will go for sure below the threshold for the creation of new pairs. At this point, the process stops, okay, and all the produced quark-antiquark will combine to form a jet of hadrons, which are of course colorless objects. So at the end of this hadronization process, okay, which was initiated by two free quarks created in the Eplasimire collision, one at the end obtained two jets, okay, of colorless hadrons, essentially back-to-back. So they essentially share the same direction of the initial quark-antiquark pair. So due to the color confinement, the original quark-antiquark cannot propagate freely, okay? And in fact, we observe this at the end as a jet of hadrons. And this process is called hadronization, or equivalently as quark fragmentation. The meaning of quark fragmentation is pretty obvious because we start from, let's say, one quark. At the end, this quark fragment into several different hadrons, okay? More in general, hadronization is a process by which a set of colored partons, either quarks and, as we will see, also gluons, evolve into a set of 4 singlet hadrons. Okay. And as I was mentioning before, the 2 jets are emitted back to back. Okay. Otherwise, momentum would not be conserved. So essentially, in the same direction, the center of mass of the original quark-antiquark pair. Now, the breakdown of the color flux and the formation of new quark-antiquark pair as the distance between them increases sufficiently can be compared with the familiar example of the broken magnet. Okay, you know, when you have a magnet with the north and south pole, you want to break it or you stretch it, at the end you get 2 small magnets, okay? And so this is essentially equivalent to what we get here when each time a string breaks into a pair of new strings. Now, of course, the probability to create quark flavors is not the same because, of course, the up and down quark are much lighter than the other. In particular, we observe a suppression in the formation of SS bar pairs as the string breaks. So essentially, due to the larger mass of the strange quark, only 20 or 30% of the cases you get SS bar pair from the vacuum. Okay. And one can also observe this suppression by looking in the final state at the ratio between, for instance, kaons and pions. Okay, the kaons contain a strange quark, the pion does not. And so the ratio in the produced yield in the final states essentially gives you an indication of this suppression factor. What about heavier quarks? So, for instance, the charmed quark. In this case, the suppression factor is totally huge. Okay, it's order 10 to the minus 11. So essentially no way you can produce a CC bar or BB bar quarks from this string break mechanism. Okay. Heavy quarks can only be produced in perturbative stage and not during the fragmentation. The fragmentation, as we will see in a moment, is essentially belongs to the non-perturbative regime of QCD. And this picture essentially depicts what is going on. So suppose we have a Eplasimire collision, okay, and you create, so they to annihilate and create at the end a quark-antiquark pair, okay. So this part here is dominated by the electroweak, so the standard model, and the QED if the energy is low, so only a photon is exchanged, or electroweak in case the energy is large enough that the process can proceed through the mediation of a Z boson. Now we have our quark-antiquark pair, and this is now the region of perturbative QCD, okay, where many many gluons are radiated, and so on. So this is where essentially the string starts to become a flux, okay, and the 2 quarks separate. Then there is a region, okay, with all these question marks, which is where the hadronization takes place, okay, and this is clearly in the regime of non-perturbative QCD. As I was telling you yesterday, in this regime, and also as we will see better today, the strong coupling constant becomes large, and so one cannot make a perturbative calculation. Okay, so there is no way essentially to know what is going on exactly here, starting from first principles. Okay, so performing QCD calculation, because you cannot do that. We are in a non-perturbative region. Alpha strong is large. You cannot use perturbation methods. And after this regime here, which is essentially the point where hadronization or fragmentation takes place, at the end one obtains the hadrons in the final states, okay, and the atom then eventually decays into lighter hadrons. And this is exactly what at the end we detect in our detector. Okay. Let me give you some example now from the LEP experiments. This Opal was one of the 4 experiments of the LEP electron-positron collider at CERN with a center of mass energy on 91 GeV, so it was tuned to the mass of the Z0. So again, we have here an Eplasimire annihilation that goes into a quark-antiquark pair, and in fact, what was observed by the experiment was a back-to-back pair of jets of hadrons. Okay. The tracks that you see here are the tracks left by the hadrons in the tracking system, the tracking detector in the inner part. They are bent because this was, of course, inside the magnetic field. And then this block that you see here corresponds to the energy released by the hadrons, either in the electromagnetic calorimeter or in the hadronic calorimeter. But it is clear that we have two jets back-to-back, okay? But there are also more complicated, more complex topologies of events where you actually observe 3 or even more, 4 jets. Okay, you see here clearly 3 jets and 4 jets. And this is the case where 1 or 2 gluons essentially are radiated in the final state. Okay, and gluons, of course, they carry color, so they cannot propagate free, as we have discussed yesterday. So also gluons have to fragment into hadrons. Okay. And so when you observe this kind of topologies with 3 or 4 jets, is because not only the quarks, but also the radiated gluons are hadronizing here. And in fact, indeed, was the first observation of a 3-jet event that was seen at the Petra experiment, at the Petra machine at DAISY in 1979, was the very first experimental proof of existence of gluons. Okay, this was the Tasso experiment. So this is the very first 3-jet event observed in the end of the 70s, and which revealed for the first time experimentally the existence of gluons. Of course, the jet initiated by gluons are different than those initiated by quarks, and this can be computed precisely in QCD. Or can be modeled, actually. It's not really a QCD, it's not a perturbative calculation, of course, because we are in the non-perturbative regime. Okay. But there are phenomenological models that allow us to make prediction how one should expect the jets originated by gluons. And there are 3 essentially indications. First of all, the gluon jets are expected to be broader than the quark jets. The multiplicity of hadrons in the gluon jet should be larger than the quark jet, so the same energy, and the particle in the gluon jet are expected to be less energetic. So essentially, when a gluon fragment with the same energy of a quark, you expect more particles which share the same energy, so each with a lower energy, and also the shape of the jet is broader. Okay, and all these predictions have been indeed verified experimentally. Now, a very useful way indeed to study QCD is through Eplasimire annihilation, so through a pure Qad process. Okay, so this is a pure Qad process where you create a quark-antiquark pair from the annihilation of electron-positron pair. But then what happened afterwards, so essentially how these quarks will fragment into hadrons, these of course belongs to the QCD framework. And what is now the advantages of using Qad to study QCD? The advantage is that in the initial state, we have essentially 2 leptons, so 2 point-like particles, okay? And when they annihilate, they just disappear. There is nothing left, just a photon, which at the end produces the quark-antiquark pair. So you don't have remnants of the initial state, which can, for instance, also hadronize. Suppose you want to study this same process, but now providing a proton and an antiproton, the observation of your phenomena will be dirty, in a sense that in addition to the real physics that you want to study, okay, there are also, you will observe many other jets which arise from the fragmentation of the proton and antiproton remnants, which are background for your studies. Okay, so the cleanest way to study QCD is indeed through a Qad process. For this reason, yeah, is what I was saying. So let's now take advantage of this and let's make some important consideration. So we've studied in the Qad chapter, we've derived somehow in the Qad chapter the cross-section, the differential cross-section for E+E- into mu plus mu minus, if you remember, okay? And we obtain these angular dependence with the cos square of theta, if you remember. Now, assuming that quarks are also spin 1/2 particle, like the muons, okay, then one expects that the angular dependence should be exactly the same for the E+E- into Q-cubar process. Okay, so one expects exactly the same angular dependence if, of course, the the angular momenta involved are the same, so the spins are the same. And this is indeed observed. Okay, so you see here now the experimental data from Eplasimire into hadrons, and this line here is essentially 1 plus cos square theta dependence. Okay, so this is fulfilled also by quarks essentially, and so this is in a way also a proof that indeed quarks are spin 1/2 particles. However, let me anticipate here that the first proof that quarks are spin 1/2 particles actually arrived much earlier, in the late 60s, through the experimental verification of the so-called Kahl-Lange-Gross relation in deep inelastic scattering, as we will study next week. Okay, so we will come back to this next week. Now, a few considerations about these results that you see here. So first of all, since the quarks, the original quark and anti-quark that are produced in the annihilation of electron-positron, they hadronize into jet of hadrons, the process is denoted as Eplasimire into hadrons, okay? In the final state, we observe hadrons, we cannot observe quarks. The second comment is that since it is usually not possible to identify which jet came from the quark and which jet came from the anti-quark fragmentation, then this ambiguity is expressed by representing the differential cross-section as a function of the absolute value of the cosine theta. Right? Now, still, let me stress again the analogy with the QAD process, with the annihilation process. So we also derived in the QAD chapter the total cross-section for E plus E minus into mu plus mu minus. If you remember, we obtained this very simple expression, where, of course, alpha m is the QAD covering constant. Now, suppose we do now the same for a quark-anti-quark pair, okay, which are fermions just like the muons, okay? So indeed, one expects that the bulk of the cross-section must be the same, and the only difference, since this is a pure QAD process, should rely on the different electric charge of quarks with respect to muons. The muons have exactly the same charge of electrons, but as we know, quarks have a fractional electric charge, okay? So we want to, we have to take this into account. And then there is an additional factor of 3, okay, which we need to put here in order to account for all possible color combination of the final state. So the point here is that in the initial state, the color is 0 because we have only leptons. And so by color charge conservation, we of course must have a total zero color in the final state, where we produce a quark-anti-quark pair. And this can only be if these come in red anti-red, green anti-green, blue anti-blue. And since all these 3 possibilities are equally probable, one has to add a factor of 3 here. Okay? So when you compare now the two, essentially the difference is just a number. Okay, this is 3 times the square of the fractional charges of quarks. The situation is actually a little bit more complicated because since the quark and anti-quark hadronize into jet of hadrons, it is not possible in general to identify experimentally the flavor of the original quarks. Were they up quark, down quark, strange quark? Hard to say just by looking at the final state hadrons. And so for these reasons, one has to take into account all possible flavor combinations, okay? Because we don't know, we cannot access the original flavor of the quarks. And this is just doing by measuring this so-called inclusive cross-section. So we are just summing up to all possible flavor that contributes. So Q, small q stands for up, down, strange, charm, etc. Okay. And now we can really compare the pure QAD annihilation cross-section with these electron-positron into hadron cross-section. Okay, and we can take the ratio of the two. And when you take the ratio, only the part in black remains. Okay, which is indeed 3 times the sum of the squared fractional charges. And so, as you understand, it is pretty simple now to test experimentally this prediction. Okay, we have just to measure the 2 cross-section, measure the ratio, and see if this corresponds to 3 times the sum of the squared charges. And in fact, this was done. Okay, but of course, this depends on the energy of your process. So suppose that you are working at low energy, so the center of mass is below 3 JeV, where 3 JeV is essentially so below the threshold for the production of Gypsie. Okay, so at these energies, only 3 quark flavors can be available: up, down, and strange. Okay, And so when you calculate the ratio, you have to consider only those three flavors. Okay, so this sum only includes the square of the up quark charge and the square of the down and strand charge. So 49, 19 plus 19. Then we have our factor of 3, which disregards the colors combination. And so overall, these results 2. Suppose now we do the same, but at higher energy, okay? So above the threshold for Gypsie or for charmonium production in general. So we have now to consider also the fourth quark flavor, the charm. And so we have an additional contribution here, which is, again, 4 divided by 9. And so overall, this number results 3.3. Suppose we can even go higher with energy, such that we can now start to excite the bottom-volume states, so the BB bar. It's not. It is a B. It's not a B. So in this case, we have an additional contribution here, and overall, the result is 3.7. Okay. So one at this point would be tempted to compare these numbers with the experimental results of these cross-section ratios. Okay. There is, however, a caveat. So one has to be careful here, because these numbers here are only for 3-level processes, but one also has to allow for higher order processes where either a photon or gluons are radiated. Okay, so indeed, if one limits himself to the 3-level values and compare this with the result, there is a 10% discrepancy with respect to experimental data. Okay, a discrepancy of the order of 10%. However, if one also takes into account these higher order processes, so higher order correction to this formula, then the agreement goes much, much better. Now, the first two are Qcd corrections, and since the alpha electromagnetic is very small, these are very small contributions, so they can be calculated easily with Qcd and very precisely, but the contribution is very small. This is clearly not the case for the gluon emission, because as we know, the alpha strong is much larger than alpha electromagnetic. So here, a first-order perturbation contribution can be sizable, and so this has to be really carefully taken into account in your calculation. And the proper way to do so is to add this term in our formula, in our ratio. So instead of having 3 times the sum of the square charge, we have 3 times 1 plus this ratio, which is essentially the alpha strong divided by pi. Of course, this has to be intended as a power expansion, so we can have an additional term which goes with the square of alpha strong, an additional term which goes with the cube, etc. Okay, but if we limit ourselves now to the first order, so 0 order and first order, then one obtains already quite accurate predictions. And so now we can compare these results, which are now corrected for this radiative effect, with experimental data, and you see the comparison here. So the points, of course, are the experimental value. We have the ratio here on the vertical axis as a function of the center of mass energy. The dotted line here are those without the radiative corrections. And as you can see, the experimental points are systematically above, 10% above. The full line are those when you fully account for this radiative correction at first order, at least. So with the correction I was mentioning before. And now you see that indeed, in this case, you are you have a very, very good agreement with experimental data. Okay. Then suppose that instead of 3 colors, only 1 color charge was possible, or essentially there were no color degrees of freedom, then the expectation would be a factor of 3 less. So one would expect the data to stay here, here, and here, which is of course in total disagreement with one observed in nature. Okay. So this striking agreement provides a very strong evidence for the existence of 3 color charges. Okay. And without this initial degree of freedom, the value of R would be a factor of 3 smaller, and so totally incompatible with the observed data. So this is a very important result, a very important confirmation of Qcd, starting from the study of a Qad process. There is also another comment here. You see the energy scale in this plot stops at around 40 GeV. Okay, of course one can go higher here, but if you go higher in energy, you don't get any more a good representation of your data, because as soon as you go higher in energy, the electromagnetic process starts to interfere with the weak process, where now the Z boson is exchanged, okay, in place of the photon. And so indeed one has to take into account this fact, okay, in order to make correct predictions. Any questions? Okay. Now, let me recall again the vacuum polarization in QED. Okay, so let me remind that as we studied in QED, at any time an electron can radiate a photon, okay, which can be reabsorbed, or the photon can create an Eplasimire pair. Each of those can create further photons, which can split again, etc. So at the end, if you remember, the net result is that your original electron is surrounded by a cloud of electrons, of virtual electrons and virtual positrons, okay? And then due to the electrostatic interaction, essentially, mainly the positrons tend to stay close to the electron, and the electron tend to be a bit far away, and as a result, one observes a screening of the bare charge of the electron, okay? We discussed this in the framework of the renormalization of QED, if you remember. And so the net result, if you remember, was that if you probe your electron at large distance, your bare charge is significantly screened by this cloud of positrons, and so you observe only a small charge. However, if you increase your energy of your momenta, you can enter more inside this cloud, and so you can probe more directly the original bare charge of the electron, and so indeed you see this charge to rise up to infinity at the zero distance. And based on this, in fact, we discussed the renormalization procedure in QED. What about QCD? Okay, so we have, of course, a similar phenomenon in QCD, but of course now dealing with the color charge. So in analogy to the vacuum polarization phenomenon in QED, quark-antiquark pairs can screen the color charge. Okay. However, there is here an important difference, because differently from QED, in QCD we know that also gluons carry color charge. Okay. And so there is a concurrent effect which arises now from the gluon loops, because not only you can have QQ bar loops, but also gluon loops in QCD. Okay. And it turns out that the effect of the gluon loops is opposite. So instead of having a screening of the color charge due to the QQ bar pair, we have in addition an anti-screening of the color charge due to this concentration of gluons, okay, close to our original quark. And so this anti-screening effect leads to an increase of the color charge at a larger distance, which is indeed the opposite effect that the one observed for the screening effect. And it turns out that in QCD, the anti-screening effect initiated by gluon loops is actually stronger than the screening effect initiated by quark loops. And so overall, this is the dominant process in QCD. And so we have indeed exactly the opposite behavior. Okay, when you probe your color field, your color charge from a large distance, so at low energy or low momenta, you observe a very, very large color field. This corresponds to a very large value of alpha strong coupling constant. On the other hand, if you increase your momentum, you go deep inside this cloud, you observe a smaller and smaller and smaller color charge at the end. Okay, and at the end, asymptotically, you reach a region where essentially the alpha strong is so small that the quark can be essentially considered to be non-interacting, so completely free. And this is indeed the regime of the so-called asymptotic freedom. We will come back to this later on. This picture just give you a representation of this phenomenon of the color anti-screening. Okay, so you have your original quarks, which radiates gluons, but gluons interact among themselves, so they create loops and loops of gluons. So when you look you probe your color charge from outside, from a large distance, okay, suppose from this circumference here, then in this very simplified, of course, picture, you see the contribution of 16 gluons, so a huge color charge. As soon as you go more inside, only 8 gluons. If you go more inside, only 4, etc. So again, as soon as you get closer and closer to your quark, the color charge decreases, and asymptotically, the quark are not interacting; they are completely free. Okay, this is the sense of the color anti-screening phenomenon. There is, of course, a consequence of this, as I was already mentioning, in the behavior of the alpha strong coupling constant. So as a consequence, and in analogy with QAD, although with the opposite trend, also the QCD coupling constant alpha S is not a constant, but it is a running coupling constant because its value depends on the energy scale. Okay, at large, it is large at small energies or a small transverse momenta, and small at high energy. So at a high momenta, so at low distance, in other words. Okay. So also the QCD coupling constant is not a constant, but it's a running constant. Its value depends strongly on the energy scale. And so as we did for QAD, also for QCD, we can make use of the renormalization group equation, okay, to find a relation that gives you the value of your alpha strong as a function of the transfer momentum Q square, okay? So one can make a power expansion in this way in terms of the logarithm of Q square divided by mu square, where mu is an arbitrary scale. So this is 1 over alpha strong at this arbitrary scale is given by 1 over alpha strong at the Q square that you want to calculate, plus we have here infinite terms in this power expansion. The situation is, as you can imagine, a bit more complicated than for QAD, because in QAD we don't have photon loops, because photon cannot interact among itself. But in QCD, in addition to quark and anti-quark loops, we also have gluon loops, okay? And these, of course, contribute to these renormalization equations. So one can stop essentially here at the first order in this expansion to get already accurate predictions, and one can then invert this formula. And when we invert, you get now the value of alpha strong as a function of Q square, given its value at an arbitrary scale mu. This factor of B, which also entered here in the previous page, indeed depends on the number of loops, okay? And so it is a bit more complicated for the case of QCD due to the presence of gluon loops. So one can compute that B is actually given by 11 times the number of colors minus twice the number of active flavors divided by a constant, where active flavors means the number of quark flavors at a given energy. So again, if we are below the energy of the Gypsie, this is just 3 for up, down, and strange. If we are above, we have also to take into account the charm, so this is 4, etc. Okay, up to 6. So once the coupling constant is known at a certain energy scale mu, okay, you put it here, and you can, through this formula, you can calculate the value of alpha strong at any value of Q square. Now, in particular, when you put the 3 number of colors, so NC equals 3, and the number of flavor is below 6, which is, of course, the standard assumption, then this B factor becomes negative. And as a consequence, you have a negative value here, so it becomes positive at the end. So as a consequence, alpha strong will decrease logarithmically with increasing Q square, which is the opposite effect that we observe in QAD. In QAD, the coupling constant was increasing logarithmically with increasing Q square. In QCD, it is decreasing, okay? Consistently with, of course, the dominance of the anti-screening effect with respect to the screening effect in QCD. Okay? Any questions? Okay. So the value of alpha strong have been measured at different energy scales, okay, just to test, of course, this QCD prediction, so the prediction that indeed the color charge is anti-screened. And let me just show you here the most precise values that we have today of the alpha strong value at 2 different energy scales. The energy scale of the Z boson, which corresponds to the mass of the Z boson, which is 91 GeV. So let's say at a large value, and the constant is order of 1.1. And at a lower energy, sorry, this is the tau, not the Z, I have to correct this. The tau lepton has a mass of 1.8 GeV, so much lower, okay? And when you calculate the alpha strong at the scale of the mass of the tau lepton, you get 0.3. So you see already how it is changing. These results have been recently obtained at next to leading order. So you put here a lot of Qcd corrections, okay, up to the 4th order. And this means including in the calculation about 20,000 diagrams. So you can imagine how complex is this calculation, okay? And the error data report that you see here are mainly due to the experimental uncertainty instead. And this figure here give you just a hint of the many measurements that have been performed and that are now available of the alpha strong. This is specifically at the mass of the Z, okay? And one can probe the value of alpha strong in many different ways. So these are now the case of the tau lepton at log Q square, or by studying heavy mesons, where QQ bar means heavy quarks, so charmonium or bothonium, or in deep analysis scattering experiments, as we will see next week, or in jets initiated by Eplasimire Annihilation, or at Hadron Collider, etc., etc. Okay, so there are many, many measures. Some are more precise, some are less precise, and the blue band that you see here is the present world average. This is updated up to 2 years ago, essentially. Okay, but this is the present value at the scale of the Z boson mass. So as I just mentioned, the predicted decrease of alpha strong with increasing Q square has been observed experimentally in many, many different ways. Okay, so by studying the hadronic decays of the tau lepton, in spectroscopy of the charmonium and bothonium states, in deep analysis scattering, in jet production, in Eplasimire, and several others. Okay, and this plot gives you now a feeling, okay, of the variation of alpha strong with respect to Q square. Okay. So the line, of course, is the QCD prediction based on the renormalization formula, and the point, okay, are experimental data taken by different, considering different, very different processes, okay, and also including corrections of next leading order, next to next, etc. So we see a clear logarithmic decrease of alpha strong increasing Q. Okay, any questions? Mi state sentendo, vero ragazzi?
Sì, la sentiamo.
Ok, va bene. Se non avete domande possiamo fare una pausa e ricominciare alle 10.
Va bene, grazie.
Va bene? Ok. Ok, riprendiamo. Vedete la slide?
Sì.
Ok. All right. So, the Aussie Rule. So if you remember, there was a topic that we left unresolved when we were discussing the hadron decay, in particular the phi meson decay. Let me just recap this first of all. So as I was showing you last week, the phi meson, which is a vector meson, has two main decay modes, in 2 kaons or in 3 pions. Okay. Now, if one looks at the energy available in the final state, so the Q value, it is much more favorable for the decay in 3 pions. So the phase space is much wider in the case of 3 pion decay than in the case of 2 kaons decay, which is only 24 MeV compared to 600. Okay, and the reason for that, of course, is that the 3 pions are light mesons. Okay, so there is a lot of energy in the decay of 5 mesons. Whereas if you sum up the mass of the 2 kaons, you almost obtain the mass of the phi. So the energy available is very small. So based on pure kinematic considerations, one would expect this decay to be much more favorable than this one here. But as you can see, one observed the opposite. Okay, and this is due to the so-called Aussie Rule. So I promised you to come back to this, and now we will come back. We will now come to this. So let's try to understand what is going on here. So the 3 pion decay, as you can see here, is represented by a disconnected diagrams. Okay, so there are no quark lines here. Okay, connecting the initial state and the final state at variance of these the other decay here. Okay, now this is the crucial point, because the phi meson, being of course an hadron, is a color singlet state. Okay, and also the final state is a color singlet state. And so you cannot connect these initial state and final state by the exchange of one single gluon, because the gluon carry color charge. Okay, so you will not get charge conservation of these two vertices here. Okay, so you cannot simply connect initial and final state of these disconnected diagrams by a single gluon exchange. Okay, and this fact is generalized by the so-called Okubo-Zweig-Lizuka rule, so known as the Aussie Rule. Disconnected diagrams require more than one gluon to be connected. And this, of course, results in an overall suppression compared to the connected diagrams. So let's now see this into more detail, and how many gluons do we need to connect this diagram. And so let me calculate the charge conjugation of the initial and final state. Concerning this part here, so this vertex here. So the charge conjugation of the phi meson is a vector meson, so one has to also take into account the spin contribution to the wave function. So as we studied a few weeks ago, is -1 L plus S. Okay. Now the phi meson is a low-lying state, so the orbital angular momentum is 0, and it is a vector meson, so the spin is 1. Okay. So overall, you get that -1 to the 1. So the eigenvalue of charge conjugation for the phi meson is -1. What about if you exchange now two gluons? So if you want to connect these two pieces with the exchange of two gluons. Now, each gluon has an intrinsic charge conjugation of -1, and this belongs to all the gauge bosons. We have a system of two gluons, so this has to be taken squared, and so overall we have a +1 sign. Okay, so we cannot match a phi meson with two gluons because we will not conserve charge conjugation. So one gluon is not possible for color conservation. Two gluons is not possible for charge conjugation conservation. However, if we now go to three gluons, okay, we overall get a minus sign here, and so finally we get the same charge conjugation. Okay, so in other words, 3 gluon exchange is the minimum number of gluon that you need to connect these two parts of the diagram. It is written here. So to ensure charge conjugation conservation and also color charge conservation, the 3 pi decay must proceed through the exchange of at least 3 gluons. Okay, And this already explained partially the reason of the suppression of this decay, but it is not the full story, actually. So let me go ahead on this. So we can now represent the decay in this way, okay? So we have now these three gluon exchanged, and each gluon is responsible for the creation of a quark-antiquark pair in the final state. So U bar, D bar, D bar. And at the end, you get the pi plus, pi 0, and pi minus, okay? Now, the suppression of the 3 pion channel with respect to the 2 kaon channel arises from the combined effect of a greater number of vertices. Of course, you are exchanging 3 gluons, so you have many more vertices, several more vertices in this diagram than in the other, okay? But this is in conjunction with a smaller value of alpha s, because as we'll see in a moment, this happened at high Q square, so at a smaller value of alpha strong. Why? Because for the 3 pion channel, the gluons must have high Q square. They are so-called hard gluons because they are produced in the decay of a rather massive meson, which is the phi. Okay, so we have the phi with a mass of 1 GeV, and this has to be converted into 3 gluons, which, of course, in order to preserve energy conservation, must be high energy gluons or hard gluons. Okay, and so the coupling constant that appear to them is small, due to the anti-screening effect that we studied before, okay? So this contributes to lower the importance of this mode in the matrix element of the decay. So not only we have more vertices, but these vertices are probed at a small value of alpha s, okay? And so these two effects in conjunction explain the suppression of this decay mode. What about the other mode? In the 2 kaon channel, only 2 soft gluons are required, this and this, okay, which share the energy of the single UU bar pair that is needed to be created, because the SS bar pair is already present in the initial state, okay? The SS bar pair is already there, it's just flowing this way. So you just need to create a light quark pair, and so your 2 gluons have to be low energy gluons, so soft gluons. And since they are soft, of course, they probe a higher value of alpha strong, okay? And so, of course, these result in a higher probability. The case of Gypsie is another interesting case where the Aussie rule is applied. So the Gypsie, the width of Gypsie resonance is very small compared to the to other harmonic states, for instance. Okay, and this corresponds to an extraordinarily long decay time for a strong decay. So the width is of the order of 0.093 kiloelectron volt, extremely small, extremely sharp. Okay, and this corresponds indeed to a decay time of 10 to the minus 21, which is very, very slow for being a strong process, right? Strong processes are usually in the range of minus 23, minus 24 seconds. So why? What is happening here? So one could think naively that the most obvious way for the Gypsie decay, which is a CC bar state, would be into a pair of D mesons. Okay, so you just create a DD bar pair from the vacuum, okay, through a gluon exchange, and then your Gypsie could decay into a D plus plus D minus. Okay, this would be the most straightforward way the Gypsie could decay. However, this is not possible due to energy conservation, because if you sum the mass of the 2D mesons, you get something which is higher than the mass of the Gypsie itself. So this decay is not possible due to energy conservation. And this, of course, tells you that the decay should proceed through a more complex phenomenology, okay? And this, of course, is first of all, is a big difference with respect to the phi meson case that we discussed before. While the phi meson is massive enough to decay into the 2 strange quarks, the two kaons, sorry, the Gypsie is below the threshold for decaying into a pair of Charmer meson. Okay, but this is a big difference between these two examples. So again, in order to have this decay, one has to consider a disconnected diagram. So the only way the Gypsie can decay strongly into pions is through a disconnected diagram, just as we've seen before. Okay. So the phase space is extremely large, because if you sum up the mass of the pions, is much smaller than the mass of your decaying Gypsie or even excited state psi prime. Okay, But the kinematic is not the full story. We have to take into account that this is a disconnected diagram, so we have to connect these with at least 3 gluons. And so we have, again, a relatively large number of vertices. And again, these gluons are hard gluons, okay, because they have to share the large mass, as energy, the large mass of the Gypsie, okay? So exactly the same argument that we discussed before for the phi apply also, in this case, to the Gypsie, okay? So the combination of the Aussie suppression for this decay and the fact that the Gypsie is below the threshold for decaying into charmed meson explain the narrowness of its resonance, and so the extraordinary long decay time. Is it clear? Hope so. Now, let's focus again on this running alpha strong issue. Okay, so when our energy scale or momentum scale is of the order of 1 GeV, so we are probing the QCD phenomena at the small energy, okay, then alpha strong is very large, order of 1. That could be 0.5, 0.6, 0.8, order of 1. Okay. And this is, as I was already anticipating yesterday, the non-perturbative regime of QCD, okay, NPQCD. The alpha strong constant is so large that you cannot apply perturbative methods here to make predictions, to make calculations. So the theory becomes extremely complex and not predictive. In fact, the low energy QCD processes like confinement, hadronization, hadron structure, hadron spectroscopy, etc., are not calculable from first principles. They need to be measured experimentally or to modeled by so-called QCd-Inspired Models. So these are models which are inspired by the QCD Lagrangian, but with some effective terms. Okay, so we have essentially a model-dependent approach in order to explain this regime of QCD. On the other hand, if you now move up to large energies, so to large momentum transfer, then alpha strong decreases quite logarithmically, okay? And at this scale, it is of the order of 0.1. So now in this regime, perturbative methods can be used, and this is indeed the perturbative regime of QCD. In this short distance regime, very precise QCD calculation, although can be performed, although they are extremely complex. And the theory becomes predictive. This is also the regime of the asymptotic freedom that I was mentioning before, where indeed the quark, so the coupling constant is so small that the quarks interact very weakly, okay, and they can be indeed considered as quasi-free particles inside the hadrons. We'll come back to this next week. However, one has to be careful here, because although a value alpha strong of the order of 0.1 is sufficiently small to allow for perturbation methods, it is not as small as the QED coupling constant, which is 1 divided by 137. And so in the case of QCD, although you can still use perturbation methods in this regime, one has to take into account higher order correction, which cannot be neglected in this case, as in the case of QED. Okay, and these higher order diagram are need to be calculated at next in order, or next to next, or next to next to next, etc. And so, in order to obtain accurate prediction, and in fact, the calculation becomes extremely complex. Okay, much more complex than in QED, where you can essentially stop your power expansion already at the first orders. Now, there is a new, relatively new approach that has been developed in the last decades, okay, which allows to make QCD calculation from first principle in the non-perturbative region of QCD. This is the technique of the Lattice Qcd, which is a non-perturbative approach based on computational techniques. So Lattice Qcd allows QCD calculation from first principle, but in a discrete grid or lattice in space-time. So instead of having a continuous space-time, you discretize your space-time, okay, like you see here in this net here, okay, And this allows you to make a precise QCD calculation, okay, but only in this discretized space-time. Of course, the results that you obtain are not physical, but the physical results are obtained by extrapolating these discrete results in the limit of vanishing lattice spacing, so in the limit of continuous space-time. So in other words, there is no way to calculate QCD precisely in the non-perturbative regime using a continuous space-time. The only thing you can do is to discretize your space-time. Then this allows you to make QCD calculation, okay? And then the physics answer, the physics results you obtain by extrapolating these results in the limit of vanishing spacing between these space-time points here, okay? Now, this is a very complicated process, okay, a very complicated technique, but is now becoming quite accurate in the recent times, okay? And for instance, today with Lattice Qcd, it is possible to calculate the proton mass from first principles. But it is a pure non-perturbative calculation with the precision already of the few percent level, okay? And also valuable results are obtained on different non-perturbative phenomena such as the confinement, QCD phase transition, spectroscopy, hadronic matrix element, atom structure, etc. Okay, so the Lattice Qcd is now becoming a really important and reliable tool for first principle calculation in the non-perturbative regime of QCD. There is, of course, a drawback, and the limitation of this technique is the computing power. The calculation, as you can imagine, are computationally intensive, and a single calculation may require several months, okay, of course, over a huge number of parallel CPUs, okay. So, of course, this calculation can only be performed on farms of supercomputers. Nonetheless, for one single calculation, you might have to wait several months, if not more, okay. Questions?
Yes, I was going to ask, this type of calculation, it's basically like, I mean, okay, like finite elements. I mean, you need the same type of machines. You need HPC basically to do this, no?
Sorry, I do understand your question. Can you repeat?
Due to the way the algorithms run, it's closer to finite elements, I suppose. So you need very parallel machines.
Absolutely, absolutely, yes, yes. Highly performant, super parallelized supercomputers, pharma supercomputers. That's the only way. And there are, in many institutions in the world, there are now such computers available. You can send your job not only at your specific place, but around the world where these facilities are available. And it is the interesting feature is that it is like for a real experiment. You know, for a real experiment, if you want to perform an experiment, you have to convince the committee of your laboratory to provide you a certain time for beam time, okay? So I need 1 month of proton beam for make my experiment. And then the committee will say, well, yes, not, depends, you have to convince him with the argument, etc. And the same is here. You want to calculate, you want to make a QCD lattice calculation, this can take months. So you have to provide the full arguments to convince, okay, the providers of this service that your calculation is really important, it's really urgent, and then you might have allocated the time that you need in your CPU time that you need. All right. I think Professor Tripiccione in Ferrara is partially involved in also this kind of business. Now, the last subject I want to discuss today is a deconfined matter, so the quark-gluon plasma issue. So in ordinary matter, quarks are confined within hadrons, and the atomic nuclei can be thought as bound state of protons and neutrons. Okay, this is the standard description. However, in normal conditions, however, as the energy density is increased, a phase transition can occur to a state in which the individual nucleons lose their identities, in the sense that the quarks and the gluons are deconfined, they become free to move across a volume that is large compared to that of the nucleon. Of course, you need a very large energy density in order for this phase transition to occur. Now, lattice calculations suggest that this phase transition should occur at an energy density of the order 1 Germi per Fermi cube. It is roughly 6 times the energy density at the center, at the core of heavy nuclei. Okay, and this can be translated into a temperature and corresponds to a temperature of the order 160 MeV. Now, clearly, these circumstances, these conditions, are believed to have occurred in the earliest ages of the universe, so in a time scale more than 1 microsecond from the Big Bang, when, of course, the energy density was so high that no hadrons could be formed yet in that epoch. At the time, quarks and gluons were completely deconfined and very weakly interacting among themselves. So they were essentially in the region of the asymptotic freedom. And they were believed indeed to form a specific state of matter that is known as the quark-gluon plasma, or QGP. So this picture shows the first instance of our universe. Okay, so we have the Big Bang here, then the time flow in the vertical direction. So as you can see, this quark-gluon plasma phase should have existed within the first microsecond from the Big Bang. Okay. Then around 1 microsecond after the Big Bang, so when the temperature of the universe dropped down to 10 to the 13 Kelvin only, then the energy density of the universe decreased under the critical value for the phase transition, and then the proton, the neutron, and also heavy and stable atoms were formed at this, in this epoch. Okay, you see here. Then after 1 second from the Big Bang, when the temperature dropped down to 10 to the 10 Kelvin, the first nuclear reactions occurred. So now we have a huge availability of protons and neutrons. So the first nuclear reaction between protons and neutrons could occur in this time here. So essentially from 1 second up to 3 minutes from the Big Bang. And this is called the Big Bang nucleosynthesis, or the primordial nucleosynthesis. Okay. And then in order to have some new important achievement, it has to wait until approximately 4,000 years from the Big Bang. This is the time now where the energy is, so that the universe is now cooled enough that the temperature goes down to 3,000 Kelvin. And indeed, for the first time, the energy of electrons and nuclei is small enough that they can produce a bound state that are atoms, of course. Okay, but the electron is now trapped in the Coulomb field of the atomic nuclei. So atoms started to be formed essentially in 3,800 years after the Big Bang, and from now on, the photons are not absorbed anymore because there are no anymore charged particles around. They are all neutral objects, which are atoms, and so the light would start to propagate freely from this moment on. And the light that you see here, the photon that you see here, is what constitutes the microwave cosmic background that we observed already today. Of course, it is now cooled down to just 3 Kelvin due to the expansion and cooling of the universe. Now, but the quark-gluon plasma is still thought to exist today in the core of the neutron stars. I guess all of you know what the neutron star is. It is the remnant of a supernova explosion with extremely high density. Okay, it is essentially made by neutrons, and in the core of these neutrons, in some of these neutrons, it is expected that the quark-gluon plasma may still exist. Now, is it possible to study quark-gluon plasma at laboratories? Yes, it is. And in fact, in the last decades, the quark-gluon plasma has been reproduced and studied in ultra-relativistic heavy ion collision. So by colliding beams of gold, or lead, etc. And this has been done mainly at the Brookhaven National Lab, so New York, and at CERN. So essentially, when you smash 2 heavy nuclei, like 2 gold or 2 lead nuclei, there is a big volume in the interaction region where essentially, if the energy density is high enough, quarks and gluons may become deconfined, and the quark-gluon plasma can be formed in this region here. So here you see a list of this kind of measurements. So the first came in the early 90s at Brookhaven with the AGS machine. So this was a gold-gold collision at the center of mass energy of only 5 GeV. Then there were the CERN experiment at the superproton synchrotron, starting in more or less the same period with the colliding now lead-lead nuclei up to 17 GeV. Then we started the era of the RIC machine at Brookhaven, okay, which is a hadron collider, still working. And they collide gold-gold at an energy ranging from 8 to 200, and now also even 500 GeV. And actually, RIC experiments, so the Star and Phoenix experiment at RIC machine, were the first to establish the formation of the quark-gluon plasma, okay, without doubts. And then the task is now taken over by CERN with the Large Hadron Collider experiments, okay, starting from 2010, as you know, and now these studies are done by colliding lead-lead nuclei with energy much higher, so up to 5.5 TeV in the center of mass. So what happened when one such kind of ultra-relativistic heavy ion collision occurs? So you collide your two heavy nuclei at relativistic energies, okay? In the collision, suppose that the collision is central, so the majority of these nucleons are involved in the collision. Then a fireball, a very hot fireball is created, okay? Where one thinks that the quark-gluon plasma is created in this region here. Now, this fireball, of course, evolves in time, so the time is floating in the vertical direction here. So as soon as times go on, this fireball starts to expand and, of course, to cool down, okay? And at a certain point, hadronization occurs. So the free quarks and gluons, which are the main characteristics of the QGP phase, then start to hadronize. And this hadronization occurs already inside the plasma, which still continues to cool down and to expand. At a certain point, after a certain temperature is reached, the hadrons finally can propagate freely, and they can be eventually observed in our detectors. Okay. This region here is dominated by the laws of hydrodynamics. So the quark-gluon plasma, as we will see, is essentially a perfect fluid. So its time evolution can be studied by using the law of hydrodynamics. So when two heavy ion collides, which are ultra-relativistics, in an head-on collision, then thousands and thousands of particles are produced in each collision. And you see here an event display picture of the Alice experiment at the Large Hadron Collider. So this essentially shows you how many charged tracks are produced. Okay, these are within the time projection chamber of the Alice experiment in a single lead-lead collision at 2.7 TeV per nucleon. Okay, so this is a real event. You have the field number, the run number, and the event number here. So thousands of particles are created in each such collision. And of course, this is a challenge for the experiments, okay? Because your detector has to be able to reconstruct all these charged tracks that are produced simultaneously. So you can imagine how complex these detectors have to be. Now, a key question is whether the energy density in the collision was sufficient to create the quark-gluon plasma and the subsequent cooling phases. So, in fact, what we observed at the end is only hadrons, okay, in the final state. So how can we say that indeed these hadrons were formed within a quark-gluon plasma? Or how can we say that we did create a quark-gluon plasma in the collision? So there are many different signatures for the quark-gluon plasma formation that have been proposed by theoreticians and that have been now extensively probed experimentally. So one of those is the enhancement of strangeness. So suppose that this is your fireball, okay, with 3 quarks and gluons, okay, so your quark-gluon plasma fireball. Now, the large number of gluons in the plasma leads to abundant production of strange anti-strange pair via gluon fusion. So essentially 2 gluons fuse and produce SS bar pairs, as you can see depicted here, okay? And this happens a lot of time because we have a huge number of gluons, of hot gluons in this plasma, okay? So indeed, one expect an excess of strange particles, such as hyperons, okay, in ultra-relativistic heavy ion collision with respect to ultra-relativistic proton-proton collision, where one do not expect the formation of quark-gluon plasma. So you can compare the yields of strange hadron produced in lead-lead collision with the yields of strange hadron produced in proton-proton collision, and one expect an excess in the case of proton-proton collision, because in the case of formation of quark-gluon plasma, this mechanism should provide a higher yield of strange baryons and mesons. You see here, for instance, the omega minus, which is an S bar, S bar, S bar, or the Xi meson, SSU, etc. And let me show you some experimental results. These from the STAR experiment at RHIC at Brookhaven, and from the ALICE experiment at CERN, at the Large Hadron Collider. And you see now the yields of strange baryons, so hyperons, the lambda, which contains 1 strange quark, the Xi, which contains 2 strange quarks, and the omega, which contains 3 strange quarks, okay, as a function of the number of participants. So the average number of participants is essentially the average number of nucleons from the 2 colliding nuclei that take part to the collision. And the larger this number, the more central is the collision. And so the smaller is the impact parameter. And as you can see, when you compare these, you make the ratio compared to the proton-proton case, you see that these quantities are above 1, okay? So we have an enhancement of strangeness, which further increases with the multiplicity, so with the centrality of your collision, okay? And similar effect is observed also so in both experiments, ALICE and STAR. So this prediction for the strangeness enhancement is very well verified experimentally. Another signature is the Gypsie suppression in case of quark-gluon plasma formation. So the production of Gypsie is expected to be suppressed because the anti-charm quarks, which are again produced by gluon fusion, just as for the strange before, this will be separated during the freeze-out by the presence of a multitude of lighter quarks, mainly up and down quarks. So essentially, gluon can fuse to create charm-anti-charm pairs, but this process is less probable, less frequent than the case of the strange quarks, SS bar, because, of course, charm quarks are much heavier, so you need very high energy gluons to provide the CC bar pairs. So this happens, but not too often. Much more often, gluons split into light hadrons, and so it is expected that the 2 CC bar that are produced are surrounded by a large majority of light quarks, up and down mainly, and so they tend to form charmed mesons, so a charm with a quark or down quark, rather than a charm with an anti-charm, okay? So during the freeze-out, the presence of a multitude of lighter quarks, mainly up and down, lead to an enhancement production of the mesons, but a reduced production, so a suppression of CC bar states. This is also observed. Let me give you some example. We have several experiments here, okay, done in the pre-LHC era, actually. And in the x-axis, you see the energy density, so GeV over Fermi cube, okay? At low energy density, so up to here, essentially nothing happens, okay? But as soon as you go ahead, so you increase your energy density above the threshold for the quark-gluon plasma phase transition, then you start to observe your Gypsie suppression, okay? Which is more and more pronounced as soon as you increase your energy density. Another mechanism that is expected to occur when quark-gluon plasma is formed is the so-called jet quenching. So suppose that a QQ-bar pair is created within the quark-gluon plasma firewall, and suppose that it is created, this occurs mainly in the peripheral region of your firewall. So you create a quark here and an antiquark there, and both quarks and antiquarks, of course, have to hadronize, so they have to produce jet, as we discussed today, right? But if this occurs in the periphery of your firewall, then you expect that one of the quarks is already close to the edge of the firewall, and so most of the jet is produced outside of the firewall, and so you observe a high-energy jet. On the other hand, the other jet, which has to be produced back-to-back, has to cross a huge portion of your high, hot, and dense matter, and while traveling through the matter, it loses energy by, for instance, gluon radiation, okay? So at the end, your jet will be smaller and with small energy. But this is the quenched jet. So essentially what you expect is that when these processes occur not in the middle, but in the periphery of your firewall, so in a certain number of events, you should expect a large, high energetic jet and a suppressed jet. And in fact, this is what it is observed, okay? So you see here an example from the CMS experiment. This is the transit momentum that in the vertical region, okay? And then you have here essentially the polar and the azimuthal angle. And so you have a huge jet, okay, with a PT of 200 GeV/c and a suppressed jet with only 70 GeV. Okay? And this is a very well-known signature observed in many different experiments. Another one is the so-called elliptic flow. So an important observable to study the collective hydrodynamical expansion of the QGP firewall is the azimuthal anisotropy in the momentum distribution of the produced hadron. So if you look in the momentum space, you expect for certain kind of collisions an anisotropic distribution of your momenta for your final state produced hadrons, okay, in the shape of an ellipsis. So it is essentially higher in this direction than in this direction here, okay? And this is a consequence of the geometrical anisotropy of the interaction region in a peripheral collisions. So if your collision between your heavy ions is peripheral, your collision volume is asymmetric in space coordinates, and this translates into an anisotropic distribution of momenta in the momentum space. Of course, if your collision is head-on, so perfectly central, then the impact parameter will be close to 0, and this will generate a very low elliptic flow because of the symmetric shape of the impact region in the initial state. On the opposite way, a very peripheral collision will also result in a small and a low elliptic flow because although the impact parameter is very large, the overlapping region is very small, so the effect is suppressed anyway. So overall, the maximum effect for the elliptic flow is obtained in the mid-central collision, like the one depicted here, so corresponding to an intermediate value of the impact parameter, not too large, not too small. And now we can just describe how this quark-gluon plasma behaves, okay? So contrary to the original expectation of a gas-type behavior, as was predicted by theoreticians well before the first experimental evidences, the present experimental results, mainly from Rick and the Large Hadron Collider, indicate that instead the quark-gluon plasma behaves as a near-ideal Fermi liquid, or in other words, a near-perfect liquid with almost no viscosity, no frictional resistance inside. Sorry. And this is the well-known Qcd phase diagram. So you have on the vertical axis the temperature, and you have on your horizontal axis the baryon density, okay? So the density of your system. Now, in the bottom left part of this diagram, this is the region where standard nuclear matter exists, okay? So at low temperature and low density, essentially. In the other region, so when you go at high density and high temperature, this is the region where the quark-gluon plasma should exist. So there is a phase transition in this border here, okay? And then there is also a critical point, which is not yet found, but is expected to lie somewhere here. And so there are many different ways to access the quark-gluon plasma regime, starting from your standard nuclear matter, okay? So the density 1 is the one that you have in ordinary nuclei. So first of all, in the early universe, the direction was opposite. So we started with the quark-gluon plasma, then there was a phase transition, and then finally, after 1 microsecond, the normal standard nucleons the bound nucleons were obtained. But today in the laboratory, we can proceed the other way around. We can try to form and excite quark-gluon plasma with these high-energy heavy ion collisions. Okay, in particular, we can do this in different regions of this diagram. So if you operate with the very high-energy machines like the Large Hadron Collider or RHIC, then you work maybe at lower densities, but you can reach high temperature. Or you can access the quark-gluon plasma from a different region, okay, where you have a larger density but a lower energy, okay? Neutron star is the place where we do expect that a quark-gluon plasma may still exist in the universe, so in nature, okay? So neutron stars are, of course, low energy systems, but high dense systems, what they say here. And then there is an even more extreme behavior of QCD, that is the color superconductor regime, which is predicted theoretically, but not yet confirmed, of course. And it is applied in the region of low temperature but very high densities. And the densities in this region are such that the quark anti-quark can collapse into a boson-like object. You are merging essentially two spin-1 fermion into one boson, QQ bar into a boson. And so essentially the quark-quark pairs behave like the Cooper pairs in superconductive. And so they tend to to collapse into bosonic states. Okay, so this is a very extreme behavior of QCD. Okay, enough for today. Any questions? Okay, no questions. So today, this lesson completes the chapter of quantum chromodynamics. We studied more formally yesterday, and now more from the point of view of phenomenology today. And next week, we will start a new chapter, which is the chapter of the nucleon structure. So we will study how can we experimentally access the internal structure of nucleons, essentially of the proton and the neutron, okay, at increasing energy. Okay, so if there are no questions, no comments, we can stop here, and we will see on Wednesday next week. And so have a nice weekend. See you next week.
Thank you. Bye.
Thank you very much. Bye-bye.
Bye.
Bye.